The world is a complex place full of unpredictable events. Chaos theory attempts to find order within these seemingly random occurrences. It explores how systems governed by deterministic laws, where the same input always leads to the same output, can still exhibit unpredictable and chaotic behavior. This is where the concept of probabilistic systems comes in. Probabilistic systems acknowledge the role of chance and uncertainty. While deterministic laws may govern the underlying principles, small variations in initial conditions can lead to vastly different outcomes. Chaos theory examines this interplay between determinism and probability, revealing the hidden order within complex systems. Imagine a game of billiards. The laws of physics dictate the motion of the balls. However, the slightest variation in the angle or force of the initial strike can result in dramatically different trajectories and outcomes. This sensitivity to initial conditions is a hallmark of chaotic systems. One of the most famous concepts in chaos theory is the butterfly effect. It illustrates the idea that even small, seemingly insignificant events can have massive and unpredictable consequences over time. The analogy often used is that of a butterfly flapping its wings in Brazil, potentially causing a tornado in Texas. This seemingly outlandish idea highlights the sensitivity of chaotic systems to initial conditions. A tiny change in one part of the system can propagate and amplify, leading to significant and unpredictable effects elsewhere. This sensitivity makes long-term prediction in such systems incredibly difficult, if not impossible. Weather forecasting is a prime example of this phenomenon. While meteorologists can make reasonably accurate short-term predictions, predicting the weather with accuracy over weeks or months is extremely challenging. The atmosphere is a chaotic system, and even minor variations in temperature, pressure, or wind speed can dramatically alter weather patterns over time. Despite the inherent unpredictability of chaotic systems, they often exhibit surprising patterns and structures. One such pattern is known as a strange attractor. Imagine a pendulum swinging back and forth. In a simple system, the pendulum eventually settles into a predictable, regular motion. However, in a chaotic system, the pendulum's motion might appear random, never repeating exactly. Despite this apparent randomness, if you were to plot the pendulum's position and velocity over time, you'd find that it tends to gravitate towards a specific bounded region in space, a strange attractor. Another fascinating illustration of order within chaos is the chaos game. Consider the Sierpinski triangle, a fractal shape created through a simple, iterative process. Start with a triangle and mark its midpoint. Then randomly choose one of the three corners and mark the midpoint between your current position and that corner. Repeat this process thousands of times, and a surprising pattern emerges, the Sierpinski triangle. This seemingly random process, governed by simple rules, generates a complex and beautiful structure, demonstrating the deep connection between chaos and order. Section 4. Fractals, nature's infinite complexity. Fractals are intricate, self-similar patterns that repeat at different scales. Zoom in on a fractal and you'll find the same basic pattern repeating itself endlessly. These fascinating structures are found throughout nature, from the branching patterns of trees and the intricate shapes of snowflakes to the rugged coastlines of continents. Fractals are closely related to chaos theory because they often arise from chaotic processes. The same iterative feedback loops that drive chaotic systems can also generate these complex and beautiful patterns. The self-similarity observed in fractals is a testament to the underlying order and structure embedded within seemingly chaotic systems. The stock market is another example of a complex system exhibiting fractal-like behavior. The fluctuations of stock prices over time might appear random. However, upon closer examination, patterns emerge. The same patterns of booms and busts repeat themselves at different timescales, minutes, hours, days, years, reflecting the self-similar nature of market dynamics. Section 5. Living with Chaos, Implications and Applications. Chaos theory has profound implications for our understanding of the world. It teaches us that even in systems governed by deterministic laws, precise long-term prediction may be impossible. The butterfly effect reminds us that small events can have outsized consequences, highlighting the interconnectedness of all things. Rather than despairing at this unpredictability, Chaos theory encourages us to embrace uncertainty. It teaches us to adapt and adjust our strategies in the face of ever-changing circumstances. By acknowledging the limits of our predictive abilities, we can better navigate the complexities of a chaotic world. Chaos theory has found applications in diverse fields, from meteorology and climate modeling to finance, ecology, and even medicine. By understanding the principles of chaos, we can develop more robust models and make more informed decisions in a world rife with uncertainty. The study of chaos is not just about understanding disorder, but about finding the hidden order within it, an order that can help us navigate the complexities of our world and appreciate the beauty of its intricate and interconnected systems.